Welcome back, everyone. So, in today's class, we are going to learn how to find out response of a multi-degree of freedom system subject to external force. We have already discussed how to find out the free vibration response of a multi-degree of freedom system. Okay, by decomposing a multi-degree of freedom system into multiple single degrees of freedom system and then combining response of each single degree of freedom system to get the total response. We are going to do somewhat similar for the forced response as well. In this case, additionally, we are going to basically represent force as sum of, or not the sum of, but a vector representation of force at different degrees of freedom, and then to represent it as a contribution of force in each mode through the diagonalization method that we have learned. Okay, so let us get started.
So till now, we have learned how to set up equation of this form. So mass matrix times the acceleration vector and then damping matrix times the velocity vector, and then stiffness matrix times the displacement vector, and now this would be equal to a force vector. Now remember, if we have a multi-degree of freedom system, and let me take the example of this, which is basically two-story shared type building we have been discussing till now, and this is 2k and 2m, and this is k and m. Okay, so let us say these are the 2 degrees of freedom we are considering, and the forces that are being applied on these degrees of freedom are basically p naught sine omega t here, and there is no force being applied here, so this is 0. So then this excitation vector can be written as p naught sine omega t and 0. Okay, so now we have to solve this multi-degree of freedom system. Remember, there would be n coupled differential equations, okay, which are basically coupled through the mass matrix, damping matrix, and the stiffness matrix. And like we did for the solution of free vibration response of Danton and damped system, what we are going to do here, okay, we are going to uncouple these n coupled differential equations by multiplying them with modal matrix phi t and writing down my displacement vector as sum of contribution to displacement in each mode. So basically un would be contribution due to first mode, let us say it is u1 plus u2 and so on, and basically this is nothing but summation, let us say 1 to n mode shape times the modal coordinate, let us say this is qr here. Okay, so what we are going to do, we are going to further write this as this is modal matrix times modal vector. Okay, so we are going to write our u vector as modal matrix times q here, and pre-multiply this equation not with phi t but basically phi t, or yeah, let us just multiply with phi transpose here, transpose of the modal matrix. So what we are basically going to get is basically this equation here, phi t m, again the modal matrix, and then we have the modal coordinate, okay, basically the modal accelerations. Then I would have this quantity here, okay, and then modal velocities, the vector of modal velocities, and then similarly for the stiffness matrix I have this here times the modal coordinate q and times phi t into p of t. Okay, Now, as we know, considering the property, the modal orthogonality of the mode, that if the two different modes are multiplied, okay, then let us say this is phi n times phi r. This is basically equal to 0 if these correspond to different mode, and same goes for the stiffness as well. And if I have a classical damping matrix, the same relationship holds true for the damping matrix as well. So basically what I get here is diagonal matrices. Okay, I get here diagonal matrices mass times acceleration vector, damping times velocity vector, okay, and stiffness times this vector, and this is equal to vector pt. Okay, all right. So this quantity here is basically your m, this quantity here is c, and this quantity is k. These all three are basically diagonalized mass matrix, damping matrix, and stiffness matrix. Okay, so the element of these matrices basically m1, m2, and mn, and same as like c1, c2, cn. We have already seen that. What do we get that as? For example, my mn is basically transpose of the shape vector for the nth mode times the mass matrix times phi n. Similarly, cn is phi nt times the damping matrix times phi n, and then kn is basically phi transpose phi n. Okay, and this is basically a new matrix, okay, for which the elements are p1, p2, p, and then so on, p and t, okay, like that, where p and t is nothing but nth mode transport times the p vector that we had assembled. Okay, so now basically what I have been able to do, reduce my n degree of multiple freedom of systems to n single degree of freedom systems, for which I'm going to just show you the spring mass damper representation. So basically I have this spring here, this damper, okay. So this is, let us say, for the nth mode, okay, this is kn here, this is cn, the mass is mn, okay, and the displacement vector becomes q and t, and the force that is being applied on this one is p and t. Okay, so basically this is the vector that you, or this is the system, the single degree of freedom system that we get by modal decomposition of the multiple degree of freedom system. So what we have been able to do, reduce my multiple degree of freedom system, which were in terms of degrees, displacement at degrees of freedom 1 2 3 as u1, u2, u3, and so on. Okay, let us say un, to, let us say this is multiple degree of freedom system in terms of n single degree of freedom system with coordinates q1, q2, qn. Okay, now remember, I would have n such single degree of freedom system, and these q1, q2, they do not correspond to any specific degree of freedom. Remember, the original equations were in terms of degrees of freedom, but here these are modal coordinates. In order for you to convert this modal coordinate to corresponding displacement at the degrees of freedom, so let us say you are considering nth contribution of the nth mode to the total displacements at each degree of freedom, you would need to multiply the qn modal coordinate with the basically the shape vector, okay, or the mode shape here. Once you multiply that, it will give you the contribution of that particular mode to the total displacement at each degree of freedom. Okay, so all these equations, when we solve these equations, this single degree of freedom system, it gives us the model coordinate, not the displacement at any degree of freedom. Okay, we convert it, and once we have for each single degree of freedom or for each mode like this, we can sum it up, okay, to get the total displacement at each degree of freedom. Okay, and we can sum it over all the modes. Okay, so this is how we basically solve our multiple degree of freedom system subject to any external excitation force. Okay, and we'll take up one example. Okay, we'll take up one example and then see how to actually get the response. Okay, so let us take the example that we have been doing so far. So what do basically we have here is this same two-story shear frame building, okay, which I'm now representing as this lollipop model here. So this is K, this is 2K, okay, this is U1 and U2 here. Now we have already derived the mass for this as mass matrix as 2m 0 0 m. Okay, I'm just going to write down here U1 U2 as well so that you don't get confused. My stiffness matrix as 3k minus k minus k and k. Okay, and on this one the external force that is being applied is p naught sine omega t at degree of freedom 1. Okay, so p naught sine omega t at degree of freedom 1, and there is no force at degree of freedom 2. Okay, so this is my excitation vector. Now what I need to find out is basically the steady state response at each for each degree of freedom. Steady state, let us say displacement response, okay, at each degree of freedom. Now before getting into that, remember when we had a single degree of freedom system in which the variable, the displacement variable was u, okay, and it was subjected to p naught sine omega t. For that, the steady state response was, so let me write down the corresponding SDOF system. If you remember, when you had an equation like this here, and do not confuse between these parameters, I'm just writing it, this is a different single degree of freedom system altogether. Okay, so when you had this kind of single degree of freedom system subject to p naught sine omega t excitation, the steady state response was ut equal to applied force amplitude divided by the stiffness of the system times 1 divided by 1 omega minus omega n, where omega n was the natural frequency of vibration of that single degree of freedom system, and then sine omega t. Okay, so this was the response. Okay, so we are going to utilize this, but now remember we are solving in terms of model coordinate q1 and q2 here, not u here. Okay, so just keep that in mind. All right, so before solving this equation, the first step that we need to do is that we need to find out the mass matrix, the diagonal mass matrix and diagonal stiffness matrix, so that I can get the generalized mass m1 and m2 for each mode and generalized stiffness k1 and k2 for each mode. Okay, so that I can write down the equation of this form: m1 q1 double dot plus k1 q1 is equal to p1, which is the normalized excitation for mode 1. Similarly, I need that so that I should be able to write down this equation as well, equal to P2. Okay, so M1, M2 can easily be found out if we write M1 as phi 1 transpose mass matrix times phi 1. And if you remember, we had already derived the mode shape and frequency for this system. Okay, and I'm just going to write it here. The frequency for the first mode was k by 2m, and the mode shape was half and 1. Okay, For the second mode, the frequency was 2k by m, and the second mode shape was -1, 1. We had normalized with respect to the top degree of freedom, which is the second degree of freedom here. Okay, so we can substitute those quantities for m1, m2, and so on. So let us say mn is this. Okay, and basically your kn is phi nt times the stiffness matrix times the phi n. Okay, so we can substitute it for 1 and 2, and we can get the normalized masses and stiffnesses as m1 equal to 3m by 2. Okay, m2 equal to 3m, and then k1 equal to 3k by 4, and k2 equal to 6k. Okay, you can do that matrix multiplication and you can check that if these are correct or not. Okay, once we have found out, let us get our the generalized excitation force for each mode. So first I want to get what is the P1T. So basically phi 1 T times the vector Pt, which is nothing but half times P naught sine omega t and 0, which gives me this as P naught sine omega t. Okay, similarly my P2T for the second mode is basically mode shape transpose, which is -1 and 1 here. Then again the same vector, and this gives me minus P naught sine omega t. So the two equations that we are solving basically becomes this equal to P naught by 2 sine omega t, and this minus P naught sine omega t. Okay, so these are the two equations that we are trying to solve here. Okay, and we can utilize this general solution to write down. Now remember what I'm going to do here. This I'm going to write as response modification factor for the first mode as R1 and for the second mode as R2. Okay, so that I don't have to keep writing the same ratio again and again. Okay, so let us do that. So Q1T is basically the amplitude of the applied force, which is P naught by 2 divided by the stiffness for that mode, which is K1. Remember, not the stiffness of the story. This is the K1 for the stiffness for the generalized modes. Okay, so 2 by K1, and I can substitute K1 here as 3K by 4, and this times let us say R1 times sine omega t, and this I would get as 2P naught by 3K R1 sine omega t. Similarly, my Q2T I can obtain as P naught or minus P naught, which is the amplitude of the force divided by K2, and K2 is 6K here. Okay, times R2 times sine omega t. Okay, so this I get as minus P naught by 6K R2 sine omega t. All right. So once we get Q1 and Q2, okay, remember the next step is basically find out the combined response. Before we get into that, since we have obtained Q1T, this is the modal coordinate, not the displacement of any degree of freedom. To get the displacement of any degree of freedom, let us consider U1T here, which is basically contribution, or if it is called UNT, contribution of the nth mode to the total displacement response. Okay, which is basically UT here. So UNT is basically obtained as phi nt times QNT. Okay, so let us first get what is the contribution of first mode to the total response, and this would give me the contribution at each degree of freedom, the displacement contribution. Okay, so my phi 1 is half 1 times 2 P naught by 3K R1 sine omega t. Similarly, my u2 I can get it as minus 1 1, okay, minus p naught by 6k times r2 sine omega 2. So the total displacement response we can get as by summing these up, okay, summing up the contribution of each mode, okay, that will give me the total displacement at each degree of freedom. Okay, so that I can write it as p naught by 6k to r1 plus r2 sine omega t and p naught by 6k for r1 minus r2 sine omega t. Okay, and this basically corresponds to the displacement history at each degree of freedom 1 and 2. Okay, all right. So we have seen that if the external excitation force is given, we can construct the force vector pt, okay, and then we can utilize the modal analysis procedure to find out the response at each degree of freedom. So this was the only focused on finding out the response at each degree of freedom, the displacement response. Okay, now it might happen, okay, that displacement response, in addition to displacement response, you might also need to find out the forces. Okay, so basically if you, let us say, it could be any type of any multi-degree of freedom system, but let us take example of a multi-story building. Okay, and let us say it's the shear type building, something like this. Okay, so multiple stories are there here, and u1, u2, the degrees of freedom are like that. Okay, so to find out basically the forces or the internal forces in the system subject to any external excitation, okay, let us see how do we do that. Okay, so remember, first we found out how to get the total displacement response using total displacement as sum of individual displacement for each mode, okay, which is nothing but summation n over all the degrees of freedom phi n and qn. Okay, and this was the modal analysis procedure that we had followed. Now let us see how to get the element forces. Okay, so to get the element forces, there are basically two procedures. Okay, and we will discuss each of these procedure one by one. So in the first procedure, we find out the contribution of the nth mode to the total displacement, u and t basically. Okay, using this, once we find out q and t, multiplying this with the mode shape. Once we found out u and t, if we know the relationship between the displacement and the internal forces, we can utilize those relationships to find out internal forces. For example, let us say this is the jth story and this is j minus 1th story. Okay, so if I define my story shear has in this story as vj, and let us say I'm considering nth mode. So in the nth mode, basically story shear in the jth story would be whatever the story stiffness is kj, let us say, okay, times the story drift. Okay, and I'll say that this is for the nth mode, so it would be kj times ujn minus uj minus 1n. Okay, and these ujn and uj minus 1 we already know from here, because remember u and t is what? It is u1 n, u2 n, so on, ujn, okay, and so on. Okay, so let us say n degree of freedom. So for the nth mode, okay, This is the contribution of the nth mode to the displacement at each degree of freedom. So we can find out this, or we can also write this as phi jn minus phi j minus 1 n times qnt. So this we can also write. Okay, so this is when we directly know the relationship between the displacements that we have obtained and the forces in the system using this type of relationship. Okay, the second relationship, the second procedure that we follow, okay, is basically the equivalent static procedure. Okay, so basically this is equivalent static procedure. Okay, and in equivalent static procedure, what do? We find out what are the equivalent static forces that are acting, and then using the static analysis of the structure, we get the forces or the story shear or the story moment at different level. Okay, so let us say I have a multi-story building like this again. Okay, so the equivalent static force is nothing but the stiffness, okay, times the unt. Now this is for the nth mode. Okay, so this can be further written as k, and this can be written as phi n times qnt. And remember, from the eigenvalue equation, this is nothing but omega n square m times phi n times qnt. Okay, so we can utilize this, and then we can find out at each degree of freedom what are the equivalent static forces. Let us say here it is F1n, F2n, and similarly at some story here, let us say this is Fjn, and so on. Okay, so the equivalent static forces at each degree of freedom in the nth mode. If we have that, finding out story shear at any level is as simple as summing up all these equivalent static forces above that level. So this would be, let us say, summation k equal to j to n and f kn. Okay, so this is summing up this f kn. Okay, and remember, I mean, we have derived this, like, given the example of multi-story building, but the same procedure would also be applicable for any other type of multi-degree of freedom system. Only thing is that this equation might differ. Okay, so let us say if I have, okay, a multi-degree of freedom system like this. Okay, and we can consider different modes of excitation. In that also we can apply, let us say if the nth mode is there, we can apply F1n and F2n like that, and equivalently we can find out what are the base shear. For example, in this case, the base shear would be, okay, in the let us say nth mode, it would simply be F1 here if we consider the equilibrium. So when we apply the equivalent static forces, we do not need to know the relationship between the displacement and the forces, okay, in the particular element. Okay, we can just consider the equilibrium of the structure and we can find out forces utilizing the applied equivalent static forces. Okay, and this can be applied for the examples to find out the forces and the internal forces and the moments in the system. All right, so we are going to conclude this lecture here today. In the next lecture, we are going to see how to apply these procedures to find out the seismic response of a structure or a multi-degree of freedom system. Thank you.